Hey there, in this video, we're gonna walk through just some basic concepts in ordinary least squares regression analyses. I'm gonna use the data that are from our regression review activity. I'm not gonna actually go through the activity in this video since that's to give you practice with it. But I'm going to use the data set, this teachcom.save data set, which is a data set looking at examining teachers' commitment to their profession and different variables that might be related with or might predict teachers' commitment to the profession. You can read the scenario here. And here's just a listing of the variables that are in the data set. So we have a measure of the teacher's commitment to the profession, the teacher's age, their biological sex, the highest degree they've earned, the number of years they've spent teaching, a measure of organizational identification, how well they identify with the organization, and a measure of job satisfaction. So if you open the data set, you can see the variable are labeled here. For gender, we have one as labeled as female, two for male. So that's good to keep in mind. Typically, whenever I have a binary variable, especially for regression analysis, I really like my binary variables coded 0 and 1. And then I like to name it the code that's 1. So I would really, we'll make males. I'll name the variable male, and then I would code it here as 0 means you're female, 1 you're male. And I think I asked you to do that in the homework, or not in the homework, in this activity. So I'll leave that for you to do in the syntax. It's not required to run a regression analysis. They can actually be coded however you like them to be the binary variable. But then it's easier reading the output. You always know that with the variables labeled male, so male is the indicator variable, and then we're comparing males to females in this case. So if the sign on the regression coefficient is positive, it's pointing to males. If it's negative, it's pointing to females. You know that by the name of the variable here. When we throw gender in there, we just have to remember that males are coded higher, so positive values relate to males. So highest degree earned, you can see ranges from associate degree to doctoral degree. Since this is a categorical variable, we would need to enter it into the regression model. We would need to dummy code the variable before we entered it into the model. And in the activity, I also ask you to do that as well. To run a regression analysis, if you don't know the syntax, you could go to Analyze, Regression, Linear. You could put your dependent variable in the dependent column, and you would put your independent variables over here in the independent column. Currently, SPSS is going to treat, if I enter education like this, it's going to treat it as if it was a continuous variable. So the regression command in SPSS will only take dichotomous or binary variables or continuous variables. Any other type of categorical variable would need to be dummy coded before you put it into the analysis. You can request some different statistics. We can get descriptive statistics. We can get some collinearity diagnostics, which gives a sense of multiclinearity. You can request plots here. We get plots of like the standardized residuals to get an idea of whether the recession, the normality assumption is satisfied. You can save out various residuals from this command, and we'll be talking about those a lot more in the regression diagnostics activity. There's not really anything in here. So we could paste the syntax into our syntax file, and it'll come up and it'll paste the syntax down here in your file. So you can see the main, so usually post it to the bottom of your syntax file, your open syntax file. You can see the command is regression. We ask for descriptive statistics. We ask for coefficient estimates. The multiple correlation, we ask for a ANOVA table, and collinearity diagnostics. You put your dependent variable on the dependent command, and then the variables you're entering go on a method command. So it'd be methods equal, and we want to enter these variables. If you want more information on the structure of the SPSS regression command, just go to the command syntax reference guide here and search for the regression command to get details about each one of the subcommands here. You can also abbreviate some of the regression commands, and that's what I've done here. So you do reg, there's the descriptives command, there's my statistics subcommand here, and I've asked for just the default statistics and then the tolerance values. There's my dependent variable, and here's my independent variable list. So you can also abbreviate it, some of your syntax as well too. So I'm just going to run this regression analysis, and we're just going to talk about maybe I need to open the data set. There we go. Okay. I forgot I just made the male variable. There we go. So the output starts off with some basic descriptive statistics. We can see we have 143 participants in this data set who have a valid case on every single one of these variables. So if you're missing, say, teacher's age, but you have a valid case, a valid response for commitment, gender, highest degree earned, all of these other items, then you'll be dropped from the analysis. So you have to have a valid case on each one. So we might want to assess missingness before we run the analysis. Here are the correlations among the variables. What you want to see in this correlation matrix, you want to see that the variables are highly correlated with the outcome and not so strongly correlated among themselves. That's kind of the general pattern that you want to be on the lookout for. This table here is worthless. It just says that these are the variables you've entered into the model. Your model summary here gives you your multiple correlation coefficient, the R squared coefficient, an adjusted R squared, and the standard error. So in this table, really what we're looking at is this R squared and adjusted R squared values. This gives us the proportion of variance explained in our outcome. That's explained by the linear combination of the independent variables in the model. So we're explaining around 45% of the variance in teachers' commitment to the profession by the linear combination of variables in this model. Is that a large amount of variance explained? It sort of depends on your field of research. In the hard sciences, physics, biology, where we have more direct control over on the variables we're manipulating, they typically have really high R-squared values. In the social sciences, our R-squared values tend to be on the lower side. This would typically be a pretty decent R-squared value. This standard error of the estimate here is, one of the assumptions of multiple regression is that the residuals are normally distributed with a mean of 0 and a constant variance. This is an estimate of the constant variance. This would actually be in standard deviation units, so you'd square this to get the estimate of the constant variance, but that's that estimate there. This is your summary ANOVA table. This is basically the same summary ANOVA table that you have in a one-way or a factorial ANOVA. This would be your sums of square in ANOVA. This would be your sums of squares between, and this would be your sums of square within or error term. So this is your explained variation and your unexplained variation. And here's your F-test. This F-test is testing. You can think of it as testing two different things. You can think of it as testing whether your R-squared, your multiple correlation coefficient here, is statistically different than 0. And so it's saying it is. We are explaining a significant proportion of variance in our outcome. You can also think of it as saying that, some combination of our independent variables are significantly related with our dependent variable, kind of the same way you think about it in like an ANOVA sense. If the F-test is significant there, it's saying that some combination of groups are different from each other. That's what it's testing here. The coefficient estimates, these are our parameter estimates from our model. And so these are, it gives you unstandardized coefficient estimates and standardized coefficient estimates. Typically you'll call these betas, or the standardized coefficient you might hear called beta coefficients. The standardized coefficients are what would happen if we converted our outcome to a z-score and converted all of our independent variables to a z-score, what the coefficient estimate would be. The unstandardized coefficient estimates are just in their raw scale of measurement. So we would interpret these, so the coefficient for teacher's age would say that for every unit increase in age, we would expect a 0.003 unit increase in teachers' commitment to the profession, holding constant the other variables in the model. So all these relationships is the relationship between that particular item and the outcome, controlling for holding constant all of the other variables in the model. We also get a significance test on each one of these coefficients. So, for teacher's age, it's saying that it's not statistically significant. So there is no significant relationship between teacher's age and commitment, which we can kind of see from the small effect here. The coefficient for gender is negative, so we have to remember that females were coded 1, males were coded 2. So this is actually pointing towards females. So you can say, and it is statistically significant. So we can say that in this sample, females tend to have a higher commitment to the profession than male teachers, or higher commitment to the profession than male professors do. The standardized regression coefficient, so it is then in standard deviation units. Standardized regression coefficients are a little weird to interpret with binary variables. It's still sort of a strength of relationship kind of a coefficient, but the Darlington and Hayes book, they really recommend, if you really want to interpret a standardized regression coefficient for a binary variable, what you should do is you should standardize the outcome and leave the binary variable coded as 0, 1. And in that case, then the unstandardized coefficient would represent sort of like a Cohen's d, a standardized mean difference between the two. So it would take the difference between males and females and their commitment to the profession and convert it into standard deviation units. Right now, this difference is in the raw metrics of commitment to the profession. So this would be the difference between males and females in their commitment to so we'd take the average of males, the average of females' commitment to the profession, and this would be their difference there. Highest degree earned here is now, we're treating it as if it was a continuous variable. And it's saying that there's no relationship. So, you know, as you increase in the type of degree you have, so you go from associate, bachelor's, master's, doctoral degree, doesn't have an impact on your commitment to the profession. It might make more sense to actually dummy code these to see, well, do people with a master's degree have a higher commitment to the profession than those who just have a bachelor's degree? You'd have to get that from actually dummy coding this, and you'll do that in the assignment. You can see here, number of years teaching was negatively related with commitment to the profession. So teachers who had been teaching for fewer years had stronger commitments to the profession than those who had been teaching a lot longer. And you can kind of interpret it the same way for organizational identification and job satisfaction. Those who are more satisfied with their job, no surprise, tended to be have a greater commitment to their teachers who are more satisfied tend to have a greater commitment to their to the teaching profession. You also get in here some collinearity diagnostics. I tend to look at the VIF here, the variance inflation factors. The tolerance is telling you the same thing. The variance inflation factor is just the inverse of the tolerance. And typically the general rule of thumb is if all your variance inflation factors are less than 5, you don't really have a problem with multicollinearity. All of our variance inflation factors are actually less than 2 here. So it's saying that there's really no problem of multicollinearity. What we mean by multicollinearity is just how interrelated our independent variables are. Remember, we want our independent variables to be highly related to our outcome, but we don't want them to be highly related among themselves. If 2 independent variables were highly correlated among themselves, then they're both kind of eating away at that same piece of variance in the outcome, and we can't really disentangle their effect. Unless it's perfect collinearity or singularity, the model will run and will estimate coefficients, but the coefficient estimates for those for the 2 variables that are for the variables that have high multicollinearity will sort of be unstable. I have a document on Canvas that you can read more about kind of the impact of multicollinearity. I would use this table here if I found that there was high multicollinearity. I would then kind of use this to diagnose where that multicollinearity is expressing itself. Usually you would look for condition indexes greater than 30 or an eigenvalue that was really close to 0. And then you sort of look across the row at these variance proportions. And if you saw 2 or more variables that had a large portion of the variance were both explained by that one dimension, would indicate that those variables seem to be the variables that are causing that multiclinearity. So here it doesn't look like, any of our, there's not two pairs of variables that that explain the a lot of variation in each one of those outcomes. So I kind of talked through, just a quick intro into how you'd interpret an OLS regression analysis in SPSS. Be sure to check out Canvas for a lot of good information on SPSS. Both the Jablonczyk and Helen, Darlington and Hayes books are great resources. And then I try to summarize some of that in some of the notes on multiple regression, some of the things to know, and it gives you about multiclinearity, the different assumptions of multiple regression that we'll cover in detail in our next class period. Also be sure to check out the review activity, the syntax starter, where I've tried to help you get kind of started with this activity. I tried to give you some additional syntax. You open your data set, you need to enter your file path here. Some code for here's how you can create one dummy variable. So I've created a dummy variable for like the associate degree. You can complete the rest of the dummy coding syntax. Interpret the regression constant. We didn't talk about that here. So how do we interpret the regression constant? Is the value of the outcome when all of your independent variables are 0. So this would be in this case, this would be the predicted teacher's commitment to the profession for a teacher who had an age of 0, a gender of 0, which doesn't make any sense because they were coded 1 and 2, who highest degree earned was equal to 0, which also doesn't make sense, who spent 0 years of teaching, who had a 0 on the organizational identification measure and had 0 on the measure of job satisfaction. So in a lot of cases, a lot of times we're not interested in the value of the constant or the regression intercept, but we could also manipulate how we enter our variables in the model, how we code them to make the constant term meaningful, and then we can get a significance test on it. So we could, maybe like center age at say like 20. So for, code gender to where females are 0, males are 1. We could dummy code highest degree earned, so that 0 represents someone who has a master's degree. A number of years teaching, we could subtract it, say from like 1 or 2, and it could be, zero represents somebody with 1 year of teaching experience. We could maybe standardize these measures, so 0 represents a standardized or the average score on it. So in that case, then the constant would be equal. So that would our intercept or constant estimate, if we did all that, would then be the predicted value for a teacher who was age 20, who was female, who had a master's degree, who has 1 year of teaching experience, and who was average on their organizational identification job satisfaction measure. So depending on how you set these up, you can get an informative value for the constant. It's not necessary that you do that. And notice you'll see in the activity that your coefficient estimates don't change, and that it's just changing your intercept value here. Here's the regression review activity. So I kind of explained to you, different options you can go through there and try to give you some syntax to get started doing that. a lot of this should be reviewed. There's a few pieces that are probably going to be new to you, like centering variables or making the regression constant interpretable. And also this idea, I think I asked you to effect code one of the variables. Will also probably be new, but the rest of it should be a review from stats too. You know, as always, if you have questions or any concerns, please shoot me an email or post them to the message board. I'm always here to help. Thank you.